Hello everyone, today I will be walking you through my deep learning project where I explored how neural networks behave under different training conditions. This project covers the five key parts, starting from data preparation to vanishing and exporting gradients, regression techniques, a custom CNN model, and final transfer learning using the VGG16 and ResNet152 architectures. So we begin by loading the raw paper scissor dataset from the TensorFlow datasets. It's a simple three-class dataset that's perfect for quick experiments. So each image is resized to 150 by 150 pixels, and the pixel values are normalized between 0 and 1, and this helps a model train efficiently. After preprocessing, I displayed a few sample images to confirm that the pipeline worked correctly. Next, I demonstrate the impact of the vanishing gradient, exploding gradients, which are the two major problems in the deep networks. For vanishing gradients, I built a deep network with 15 sigmoid layers. Because sigmoid compresses the gradient values, they gradually shrink as they backpropagate and the model stops learning. So you can see that the accuracy curve stays flat, close to the random guessing at about 33%. And for the exploding gradients, I use the ReLU activations but initialize the weights with very large values and a huge learning rate. This caused the loss to actually instantly become NaN, showing how gradients can blow up. Together, these two experiments visualize why careful choice of activations and initializations are to be important. In the next part, I trained a small CNN to observe the overfitting. The training accuracy went up quickly, but the validation accuracy um, stayed lower, meaning the model memorized the training set. To fix this, I did the regression techniques like the data augmentation with random clips and rotations, dropout layers uh, to randomly deactivate the neurons, and alter regularization to control the large weights. After applying these, both training and validation curves become smoother and much closer, proving that regulation improves the generalization. As you can see this, okay. And then after that, I designed my own custom scene architecture from scratch. It included three convolutional blocks, batch normalization, and the dropout layers. The model trained stably, but reached about the custom text accuracy of about 35.75%. This shows that while it learned some patterns, it wasn't deep or express enough. And architecture design plays a major role in the final performance. Finally, I use the transfer learning with two pre-trained models, which are VGG16 and the ResNet152. Both were originally trained on ImageNet, and I froze the convolutional basis and added new dense layers for a three-class task. VGG16 gave the good results, but ResNet152, thanks to its residual connections, achieved the highest test accuracy overall. This clearly shows the power of the pre-trained deep networks, especially when working with the smaller datasets. To summarize this, the project walks through the entire learning journey from understanding the gradient problems to preventing overfitting to applying advanced architecture for classification. It highlights how every design, choice, activation, calculation, or architecture depth directly affects the model performance. Thank you.